Hello students, and welcome back to another geometry video. Now at the beginning of each chapter, the question is a little bit different. Instead of being a question just like last time, I like to ask a question that opens up what we're going to talk about in this chapter. Now I know 2.3 isn't typically the beginning of a chapter, and if you're watching this years from now, I probably have 2.1 and 2.2 up by now. But for now, we're going to start the chapter with 2.3. Being online, being virtual this year has made things so that we need to cut some stuff out. So we cut out 2.1 and 2.2, but we're going to pick it up with 2.3. So, what can you conclude from this diagram? What can you not conclude? So 2.3 today is all about looking at diagrams. What do you know by looking at this diagram? What do you think? Do you think we can say that ADB is a perfect right angle? No, I don't. It doesn't say that it's a right angle. So, if it doesn't say it, it can't be a right angle. Which means I don't know if these are complementary or not. But I can tell that this is the vertex of everything. B is the vertex of everything. So, these rays intersect this line at point B. I know that. Not much more. I mean, A, B, and C are collinear. Because this is a line, I can tell that they're collinear. What more can I say? Well, let's take a look. I stole this from the book. So you can conclude, that all points are coplanar. Because this is a flat surface, we're in 2 dimensions. All of these points are in the same plane. You can conclude that they are all in the same plane. Yeah, points A, B, and C are collinear. We talked about that already. And yeah, that they intersect at point B. We talked about that. Adjacent angles and straight angles. We can conclude that. And that point E is in the interior of this angle. Yeah. So that is all clear because you can see it in the diagram. Things you cannot see in the diagram: AB congruent to BC. If you do not see those tick marks, we don't know if they're congruent. You cannot assume they are congruent unless you see those tick marks. Angle DBE congruent to angle EBC. Yeah, you have no idea. They look like they could be the same, but if you do not see these tick marks, you don't know. You don't know that they're the same. And yeah, we did talk about how unless you see this right angle symbol, unless you see the box in the corner, you cannot say that this is a 90-degree angle. So this is a fun, I think, introduction to what we're going to talk about today. What we are going to talk about today. I know typically I don't address the essential question, I just have it up there for you, but what 2.3 is all about is, in a diagram, what can you assume and what needs to be labeled. Like how we talked about, this little right angle box better be labeled, and if it's not labeled, we don't know if it's a 90-degree angle or not. It could be a 90-degree angle, but we don't know. Unless we see this box, we don't know if it's a right angle or not. So, what 2.3 is all about is, in a diagram, what can you assume and what needs to be labeled? Well, postulates, you've heard us talk about the ruler postulate, the protractor postulate, things like this. A postulate is something that we just accept. You don't have to prove it, we can agree on this. It is clear that this postulate is the case. I don't have to prove it. I don't have to argue with you, oh yeah, but no. It is. A theorem is something that has to be proven, and we'll talk about theorems later. But for now, we're going to look at a lot of postulates. In 2.3, we're going to look at a lot of postulates, and then those postulates are going to help us decide what we can assume and what needs to be labeled. So, our learning target for today is that you know what the point, line, and plane postulates are. There are many of them. And our success criteria is that you can identify postulates from diagrams and use postulates to interpret diagrams. So if you start with a diagram, you can find the postulates, or if you start with the postulates, you can create the diagram, or you can see them in the diagram. Okay, so let's jump right into it. There are many postulates, many postulates, but they all make a good amount of sense. So I'm going to encourage you to write these down. If you're like, no, that 100% makes sense, I know exactly what you're talking about, maybe you don't need to write all of it down. But for me, I don't get things the first time around. I don't just like read it and understand it. I have to write it down and I have to revisit it and come back to it again and again before I understand. So if you're like me and you take a little bit of time to understand things, please write these things down, these postulates. You don't need to, if you want the example, you can, but the postulates are what I'd encourage you to write down. But if you're just like, no, these absolutely make 100% sense, I'm not going to write them down. It's up to you. Okay, so the first postulate, postulate number 1, is the 2-point postulate. And what it says is that through any 2 points, there is exactly one line. I've actually mentioned this before in chapter 1. If you have 2 points, I can only draw one line in between those 2 points. There is no, that's not a line. That's curved. Lines are straight. So there is only this line that I can draw through these points. If I draw this line, it's not going through this point. So between any 2 points, there is only one line. Now the line point postulate, this is postulate number 2, the line point postulate. A line contains at least 2 points. So if I have a line, there must be at least 2 points on this line. There could be 3, there could be 4, there could be 18 million. There could be as many points as you want, but there must be at least 2 points on each line. So a line contains at least 2 points. And this, of course, is what a picture of them looks like. And an explanation of the example. What I want you to write down is this, though. I want you to write down the postulates themselves, because all the homework for today is going to require these postulates. And as I'm doing the examples, I'm going to have the postulates up in front of me so that I can see them. All right, moving on to postulate number 3. This is the line intersection postulate. And what it says is that if 2 lines intersect, their intersection is exactly 1 point. And you can see this here. These 2 lines are crossing, and the only place that they cross is that point. No matter how you draw 2 lines, there is only 1 point at which they intersect. No matter how you draw the lines, they intersect at 1 point. They cross at 1 point. And that's what this example says. Or excuse me, that's what this postulate says. If 2 lines intersect, their intersection is exactly 1 point. No more, no less. 1 point. Postulate number 4 is the 3-point postulate. So now we're going to talk about planes. We said point, line, and plane postulates. So these postulates are going to talk about planes. Through any 3 non-collinear points, and we talked about this in chapter 1 actually, the thing that makes a plane 2-dimensional is that you have 3 non-collinear points. The 3rd point is what gives you that 2 dimensions. If I just have 2 points, I have a line. If I have 3 points, now I have a plane. So, through any 3 points, there is exactly 1 plane. There's only 1 plane I can draw this in. And this would be better visualized in 3 dimensions, but unfortunately you're watching me in a video, and I am only in 2 dimensions in this video. So, there is exactly 1 plane for any 3 non-collinear points. And a plane contains at least 3 non-collinear points. So it could have 4, could have 5, could have a million, but it has at least 3 points in it. So these are very similar to the first two that we had. Any 2 points make one line. Any line has 2 points. Now, through any 3 points, there's one plane, and every plane contains at least 3 non-collinear points. And that was postulate number 5. Okay. I think there's 2 more postulates. There's 2 or 3 more postulates. I told you there was a lot. This is postulate number 6, and it is the plane line postulate. So now we're combining planes and lines. So, if 2 points lie in a plane, so D and E are in plane R, then the line containing them, line DE, is also in this plane. So, if I have a plane, that means that I have at least 3 non-collinear points in it. This line is in the plane. This line is in the plane. Oops. This line is in the plane. All the lines made by connecting the points in the plane, these lines are in the plane. Even if the arrow goes outside of the boxed picture, remember, these extend forever. So this side of the box actually extends much further, just like this line extends much further. So it doesn't matter if the arrow is sticking outside of the box or not. If 2 points are in a plane, the line made by connecting those 2 points is also in the plane. Hopefully you're writing these down. Okay. And next, one more postulate. Last postulate. Postulate number 7 is the plane intersection postulate. So we talked about lines intersecting. When 2 lines intersect, their intersection was 1 point. Now, when 2 planes intersect, their intersection is a line. And you can tell, you can kind of see that in this picture. S is like a piece of paper. Plane S right here is like a piece of paper that you hold vertically. You got a piece of paper vertically right here. And plane T is like a piece of paper held horizontally. And so if you take those 2 pieces of paper and you put them together, that whole line across the piece of paper, it's not just a point, it's every point along that piece of paper. So, oops, I want a different color. So every point on this line is at the intersection of those 2 pieces of paper, or the 2 planes. So 2 lines intersect, you get a point. 2 planes intersect, you get a line. So see how when 2 lines, remember lines are 1-dimensional, and their intersection is a point, which has 0 dimension. Planes are 2-dimensional, but their intersection is a line, which is 1-dimensional. So the intersection of 2-dimensional figures gives you a 1-dimensional figure. The intersection of 1-dimensional figures gives you a no-dimensional figure. I thought that was interesting. Okay. That is all of our postulates. Now, we're going to do some examples using those postulates. So, example number 1 says, state the postulate illustrated by the diagram. So, part A says, if 2 lines are crossing, that's just what I see. I see 2 lines crossing. So, if 2 lines crossing, then what's the difference between these 2 pictures? Oh, there's a little point. There's a point right here in the middle. So if 2 lines cross, then there's a point in the middle. If 2 lines intersect, then what? Which postulate was that? I gotta go through them. It's the line intersection postulate. It's postulate 2.3. The line intersection postulate. It says if two lines intersect, then their intersection is exactly 1 point. So it says to state the postulate illustrated by the diagram, so I suppose you could have just said postulate 2.3, the line intersection postulate, but it's more important to me. I don't care if you memorize the names of these postulates. You can figure out the name of the postulate if you remember what the postulate says. If two lines intersect, then their intersection is exactly 1 point. Lines intersect, line intersection postulate. So I care that you remember what the postulate says. I don't care that you can recite their names. Okay, let's do question B. If, let's see, I see two planes. This is a plane, and then there's another plane. So if two planes intersect, oh my goodness, intersect. You have no idea how hard it is to write on a computer screen. Maybe you do. Okay, but if two planes intersect, then I see they have this red line highlighted. So if two planes intersect, then this is, which postulate is this? This is postulate number 2.7. The plane intersection postulate. And it says if two planes intersect, then their intersection is exactly 1 line. Cool. If two planes intersect, then their intersection is exactly 1 line. So we stated the postulate, we stated the name of the postulate, and we stated the postulate in words. So cool. Let's see if we were right. Booyah. Line intersection postulate, plane intersection postulate, and they even said the words, just like we did. Beautiful. Example number 2. Identify postulates from a diagram. So now they're telling us to use the diagram to write examples of the plane point postulate and the plane line postulate. I gotta go back and see what those postulates were. The plane point postulate. Okay, different colors. The plane point postulate said, and I mean, I could scroll back up to it over here too. It said plane point postulate right here. A plane contains at least 3 non-collinear points. Back to the example. Ooh. So a plane contains 3 non-collinear points. Okay, and we need to write examples of this. Well, an example of a plane containing 3 non-collinear points is, look at plane P. Look at plane P right here. What are the points inside of it? Plane P contains point B, point A, and point C. Has 3 non-collinear points. So plane P contains points B, A, and C. That's an example of the plane point postulate, because the plane contains 3 non-collinear points. So we have written an example of it. Beautiful. Next, it wanted an example of the plane line postulate. Now, what did the plane line postulate say? Aha, plane line postulate It says if 2 points lie inside of a plane, then the line containing them is inside of the plane. Oh, so this is what we talked about. If I connect any 2 points inside of a plane, that line is in the plane. Okay, back to the example. So let's see, these 2 points have a line. So, okay. So because B and A points, because points B and A are in plane P, then line BA, we also could have called it line N, doesn't matter. Line BN is also in plane P. There you go. That's an example of the plane line postulate, because it said if 2 points are in the plane, the line containing them is in the plane. Let's check if we were right. P contains at least 3 non-collinear points, A, B, and C. And point A and point B lie in plane P, so line N, containing points A and B, also lies in plane P. Yay! Okay. Example 3, sketch a diagram. So I know that there's a lot of examples here, but they went pretty quick. Once you know the postulates, the examples go pretty quick. So that's why I encourage you to write down the postulates, know the postulates. Again, you don't have to memorize exactly each word of them, but understand what they say. Okay. Sketch a diagram showing line TV. Okay. I can make a line TV. Intersecting PQ, segment PQ, at point W. Okay. Actually, let's make this diagram bigger. All it's asking us to do is sketch a diagram, so we can make this as big as we want. So this is line TV. That is supposed to intersect with this segment. Segment PQ. And that looks perpendicular, but it doesn't have to be. Now it's intersecting PQ, segment PQ, because there are no arrows up here, at point W. So they intersect at point W, so that, different color now, so that TW is equal to VW. Ah, so we want to draw the picture so that these are the same. Okay, TW looks a little bit bigger than WV, so I am gonna move point V over here. And now they look the same, and even if they're not perfectly the same, I put tick marks there. And remember, these tick marks mean congruent. So, that diagram is perfect. Now, you don't have to color code. I am a color coder. You probably know this by now. I'm going to keep color coding because it helps me. So you can draw this all in one color and it will be the same thing. But the important thing is TV is a line, and we have the arrows making it a line. PQ is a segment, and we have the endpoints making it a segment. And W is at the intersection. We did that. And TW is congruent to WV. We did all of that. So, our diagram is perfect for this statement right here. There we go. Let's check if we were correct. Yeah. Step 1, draw TV and label points TV. Step 2, draw point W, draw PQ, mark the congruent segments. Yeah. We did all of that too. And of course, there's another way. It says there are many ways you can sketch the diagram below. It could look like this, it could look like this. As long as you checked all the boxes, TW and VW are congruent, One's a line, one's a segment, they intersect the W. As long as you check all those boxes, you have the right answer. You have created a correct diagram. It doesn't matter if the diagram looks exactly like theirs or not. Okay. More important information before we begin our next couple examples. A line is perpendicular to a plane if and only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects that point. So basically, in a diagram, a line perpendicular to a plane must be marked with a right angle symbol. So this right angle symbol. And here, this right angle symbol here is talking about lines T and P, and this right angle symbol here is talking about lines T and Q. But because this line is in this plane, and line T is perpendicular to this line, it means that T is perpendicular to the entire plane. So if line T is perpendicular to a line in a plane, it's perpendicular to the whole plane. Okay. Alrighty. Now, example 4, interpreting a diagram. This is basically what we did in the entry task. Can you conclude, or excuse me, can you assume these things from this diagram? So it's going to give us statements, it's going to give us a statement, and we have to decide, can I assume it or can I not assume it? And unless the diagram tells us, we can't assume it. So, points A, B, and F are collinear. Points A, B, and F are collinear. They are all on the same line. And that's what it means to be collinear, is for all of the points to be on the same line. So yes, can assume. Because it's right there in the diagram. A, B, and F are on the same line in this diagram. It's right there, so we can assume that. Okay, next, points E, B, and D are collinear. Okay, points E, B, and D are collinear. We don't know that. There's no line. I don't see a line connecting those points. Do you? I don't see them. It might look, maybe, I drew a pretty straight line. Maybe they would be collinear, but there's not a line through them. And because there is not a line through them, I cannot assume this. Can't do it. Okay. Next, is line AB perpendicular to plane S? Line AB is right here. Is that perpendicular? Is this perpendicular to plane S? And let's see, plane S is this plane right here. Look at this. What is that? That's a right angle. That's a right angle box. So yes, you can assume. Because they give us that right angle box. If we didn't have this right angle box, you don't know. You have no idea if they're perpendicular. Oh, and that's what this T means. I'm sorry. I might not have said that. This upside down T, this means perpendicular. You're going to see that a lot in this chapter and in subsequent chapters. So, in chapters in the future. So make sure that you know this. Write it down. The upside down T means perpendicular. Okay, now for the next one. Line CD is perpendicular. Remember, that's what the upside down T means. Is perpendicular to plane T. So now, CD is right here. And plane T is this box right here. Are they perpendicular? CD, plane T. They can't be perpendicular. CD, oh, ha ha ha. CD, I drew the wrong line. No wonder I was confused. I drew line CB, not line CD. Whoops. Everybody makes mistakes, even in math. The math teacher makes mistakes. Okay, so line CD. Is this perpendicular to plane T? Well, do we have a right angle box? I don't see one, so no. You cannot, whoops. You cannot assume. All right, last one. Line AF. See, okay, AF is right here. Intersects BC. Line BC is right here. At point B. Well, yes, that is right in the diagram. I see line AF, I see line BC, and they are intersecting. I can see it in the diagram, so yes, I can assume this. If you can see it in the diagram, you can assume it. Okay, let's check our answers. We had yes, no, yes, no, yes. And they said, cannot assume they're collinear, cannot assume, so they only had 2 cannot assumes, and so did we. We had 3 yeses, 2 nos, and they also had 2 nos. So yay. Okay. Woo! I know that was a lot of examples. I hope that you saw that the most important things from this lesson were using the postulates. It's not just memorizing the postulates, it's being able to apply them. What does this postulate mean? And what does it mean in this diagram? So make sure that you're not just memorizing the postulates, but you know what the postulates mean. And if you have questions about any of that, Chapter 2, I think, lays the foundation for the logical reasoning of, Chapter 2 is literally all about deductive and inductive reasoning. And that's why we teach geometry. That is why geometry is a math class, is because logical reasoning is the most important part of math. And in algebra, you're so focused on learning how to solve in the different ways, which is very important, especially if you get farther along in math. It is very important. I'm not saying algebra is not important. But geometry does a better job of making you think logically than algebra does. And that's why we teach geometry. So I hope that you're thinking a little bit harder and that you're thinking logically. If this, then this. If this, then that? Yeah, then that, you know? Okay, and if you have questions, get those questions answered. Talk to your teacher, talk to your friend, talk to me, do whatever you need to do. Okay, practice problems. Yeah. All of them are on this slide. I thought maybe we had another slide of practice problems, but no. These are the practice problems. You can see example 1, example 2, example 3, and example 4. Remember to still do the homework that your teacher assigns. Don't just do these problems. But these problems will help you practice all the skills you have learned in this video. And now, as usual, let's end our video with a launch, shall we? Today's launch comes from Camila A-Ring Kimball. I probably butchered that, I apologize. But she says, you do not find the happy life, you make it. And I like this a lot because my life has not been super happy. If you ever get to know me a little bit more, there have been some not so fun things that have happened in my life. So if you just look at it that way, it's not a happy life, but no. I make it a happy life. I have taken the crap that I have been given, all the bad stuff that has happened to me in my life, I've taken it and I've made it what I want to. I'm not defined by the high school bullies. I'm not defined by abuse. I'm not defined by any of that. I can make my life happy no matter what happens. And I'm not saying that if you're in a horrible situation, you just need to be happy. That's not what I'm saying. But what I'm saying is your life is going to be a long time. And this situation that you're in right now is not going to last your whole life. So when this situation is over, and maybe you can stop the situation, maybe you can't. Maybe you can get out of it, maybe you're stuck for a little bit. I've been in both of those places. But you can change your life. Your overall life does not have to be bad because this section of it was bad. You can change it, and you can make it happy. So, I encourage you to make your life happy when you can. Sometimes it just has to suck, but you can change it. You will get to a point in your life where you can change it, and I encourage you to do that. That is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thank you so much for being here. Thanks for watching. Bye.